Okay, kindly consider the following differential equation. dv dt is negative g. That's a differential equation, an equation with a derivative in it. How do you solve it? You find the function whose derivative they're talking about. What function am I looking for?
T of v.
Not t of v, the other way around, v of t. Right? I'm trying to find v of t. All right, so what we usually do, we're going to be analytic this week mostly. The analytic approach here is to like cross multiply, get the v's and the t's separated. We call this variable separable differential equations. There's a whole ton of different kinds of differential equations that come up in nature that you have to figure out how to solve them, and there's a lot of analytic techniques. We're going to focus on variable separable. So how do I separate this? Well, if I cross multiply, I get dv is negative dt, sorry. Okay? Now g is just a constant. Yeah?
You said variable separable?
Variable separable. We're separating the variables v and t in this case, right? I'm going to set up so I can integrate with respect to v, so the dv has to be in the numerator. And I want to integrate with respect to t, so the dt has to be in the numerator. Have you ever seen a dt in an integral in a denominator? No. Doesn't make any sense, okay? So that's what we did. Now, what this is a differential equation modeling Galileo's freefall model. In other words, you fall out of an airplane. How does your velocity change? The rate of change of your velocity is also known as the acceleration. Our acceleration is negative g, the acceleration due to gravity. Why is it negative? Well, I'm talking about in a frame of reference where negative means you're moving down. Okay? So your velocity becomes more and more negative, right, as you fall down. So how do you get rid of the d? Well, this is just a derivative, right? So integrate both sides. And you get these cancel, and you get what? What do you think you get over here? What's the antiderivative of a constant dt? The t, right? I'm going to say the constant, which is negative g, times t. Isn't the derivative of this negative g? Remember, I'm looking for an antiderivative. The antiderivative is the derivative of what I started with. The derivative of the derivative of the answer is what I started with. The derivative of negative gt is negative g, isn't it? Right? If this said like negative 2, you'd get negative 2t. Right? Is that terrible? Don't forget, there's a constant though. Now here, the constant is important. Okay? So like I said, this is a Galilean freefall model. So let me give you some information. It says a stone is dropped from a 100-foot high building. Okay? So I'm standing outside, on the roof of a 100-foot building. I take the stone and I drop it. Hopefully my enemy is walking by, right? So, okay. Find as a function of time its position and velocity, and when does it hit the ground? And how fast is it going when it hits the ground? Okay? So there's your velocity, but how do you find c? Can you resolve c? Do you know what the constant is? Now think about it. We're talking about the velocity as a function of time. Do you know the velocity exactly at some point during the fall of the stone? It's 0 when? At the beginning, at t equals 0, right? So I have what's known as an initial condition problem, or an initial value problem. I'm going to solve this differential equation, and I'm going to get a general solution, right? But I also want a particular solution. Knowing that v of 0 is 0, I can figure out what c is. All right, so plug in. V is what? 0. That's this 0. And t is what? 0. That's this 0. I'm plugging in for t, right? So there. Plus c. Now this is sort of silly, but whoops, this is a c. This is sort of silly, but what's c? It's 0 because that's 0 and that's 0, so c is 0. It doesn't always have to be. Sometimes c is something important you need to know. Okay? So your general solution is this, but your particular solution is v is negative gt plus 0. You don't have to write the plus 0, but there you go. All right, so there's your general solution, a whole family of curves, a particular solution, the one curve that goes through that point. Now you know the velocity. Okay? Now, by the way, do we know g? We were given the information in terms of feet, right? The stone is dropped off of a 100-foot building. Do you know g in the English system? in feet per second, 32, right? So while I say g, I could be talking about, I could say it's 32, right? So let's say this is negative 32 feet per second, and this is negative 32 feet per second, and this is negative 32 feet per second. Realize that it's different if you're not, at sea level on the Earth. What if you're on the moon? What if you're on a mountain? It could be different. So for this particular problem, I'm not going to say g in general. I'm going to say negative 32 feet per second. So there's your velocity curve, okay? Now what's your position curve? They want to know how far you've fallen over time and when the heck you hit the ground. How are you going to get a displacement curve? How are you going to get an S of t? Some people use that as displacement, S for displacement. In this case, it's vertical motion, maybe y of t. This is a velocity, right? Isn't the velocity itself a rate of change? It's dy dt, let's say. It's the rate of change of how far you're falling. So I'm going to say now, I know that dy dt is negative 32t. But I have an initial condition here too. Do I know any position along this trajectory? How high off the ground I am for some particular value? Wow. What's going on? I'm getting echo. My mic is feeding into another mic. But there's only one mic. Yeah, but is that going to mess me up on my recording? Hello? Yeah, maybe I should turn down something. Let's turn this down. Hello, hello, hello. Hello, hello, hello. Is it still doing it?
Still doing it, definitely. Exactly.
It's coming out of there, I think. So I don't think that's going to affect this.
It's going to affect me. I don't know if
It's going to affect you? Why is it doing that? That's weird. All right, well, where's the thingy? Where's the little thingy ahead? There it is. Let me turn down the volume on this thing. I think it's coming out of there. So if I turn down this volume. Hello, 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 hello. I'm going to turn down this volume because I'm not recording from here.
Yeah, that sounds fine already.
I'm okay? Yeah? Hello? Okay. That's weird. That never happened for 12 other recordings. What the hell? Okay, so it has nothing to do with where I am, right? Hello, hello, hello. Hello, hello. Okay, I'm good. Okay. So what's the initial, this is an initial value problem because I'm trying to find y as a function of t, but I know one value on the y curve. Y of what? 0 is when I dropped it. How high was it, did I say? I was on the roof of a building that was 100 feet high, okay? So there's my initial value, my initial condition is that y of 0, how high up off the ground I am, is 100 feet. Yeah, that was good. Okay, there you go. So now can you get the displacement curve, y of t? How do you variable separate this? Can you get the y's away from the t's? There's only two variables here. There you go. dy is negative 32t dt. Now anti-differentiate both sides. And the antiderivative of the derivative, that cancels. What do you get? Y equals. What's the antiderivative of t dt? T squared over 2. So negative 32 t squared over 2 is really, negative 32 t squared over 2 is what? Negative 16. T squared plus another constant. Now look, this thing about calling the constant plus c all the time is going to get confusing because that plus c and this plus c are not the same plus c. So it doesn't have to be plus c, all right? You'll live with plus a, okay? I'm going to call it something else. So how do you get a? Can you get a? Because this is the general solution to the differential equation, but I want the particular solution if I can get it. The one curve that has this behavior but goes through this point. So how do I get a? I know that y is 100 when t is 0. Okay. So plug in 100 and plug in 0. And what is a this time? What's the constant of integration this time? A is 100. So now you get that y of t is negative 16t plus 100. T, whoops, what did we say? T squared. Whoops, sorry. T squared plus 100. Okay? All right, so let's answer the question. When did it hit the ground? How do we find out how long it took to drop to the ground? When who's 0? When y is 0, it's solve for t right there, right? Okay, so if I plug in y is 0, I can figure out t is when does it hit the ground, because y equals 0 is the ground. Y equals 100 is the top of the building, right? So if I plug in 0 for y here, I can solve for t, and then I can go back here and plug in that time to figure out how fast it's hitting the ground, because I want to know how hard it's hitting the ground, right? How fast it's going. All right, so let's find that time. When is y 0? How do you solve for t here? Subtract 100, okay. Divide by negative 16, and the negatives are gone, and get t squared is what? 100 over 16, right? But that's t squared. So t is what? 10 fourths, or 5 halves. 10, right? It's just square root the 100 and square root the 16. Or 5 halves, or 2.5 seconds. Okay? 5 halves or 2.5. All right, so it's 5 halves seconds. It took 5 halves of a second, or 2.5 seconds to hit the ground. That was the part A. Part B is how fast was it going when it hit the ground? How do you figure that? Plug in that time into the velocity curve, which is there. So we need v of 2.5. Okay. Since v of t was negative 32t, where there's a 5 and that's a seconds. Yeah. So v of 5 halves or 2.5 is negative 32 times 2.5. Let's see, half of 32 is 16, 2 times 32 is 64, 64 and 16 is what, 80? Right? So I get negative 80 what? What are the units for velocity here? Feet per second, right. So it's going pretty fast, negative 80 feet per second. What's the negative mean? It's going down rather than going up, that's all. Okay? Is this terrible? And this is the essence of what is a differential equation and how do you solve it. And that's all we're focusing on today. Tomorrow, 7-1, we're going to focus on anti-differentiating stuff that came from the chain rule. So how do you unchain rule something? We're going to need that, okay, on Wednesday. Alrighty then. Let's see. All right, let's wait. Let's just practice this up. Let's go straight to the homework page, okay? Straight to the homework page, practicing this up. All right, so on page 315, number 1. Now the first few questions, I'm just going to get some general solutions to the differential equations, right, 1 through 4. Later on, they'll give you some initial conditions, 6 through 10, so you get some particular solutions. And then after that, 11 through 28, you have a whole bunch of word problems where they give you a differential equation with initial conditions, or they give you the words and you have to write the equation. Okay, one thing at a time. So really our focus this week is using integrals to solve differential equations. It's really our focus. All right, so number 1 on page 315, let's try it. Now, this is just practice. We don't have an initial condition. We don't have a word problem or anything like that. Okay, so this is section 6.3. Let me get some color here. What's going on? 6.3, and it's page 315, number 1. All right, so in exercises 1 through 4, find the general solution for this differential equation. dy dx is x cubed plus 5. Remember, this is a differential equation because there's a derivative in it. So how do you solve it? You get rid of the derivative. You got to get y as a function of x. How do you separate this? That's it. It's cross multiplying. Usually that's all it is. All right, so you get dy equals x cubed plus 5 dx. All of it times dx, right? Usually it's just cross multiplying. Sometimes it gets a little more fancy. We'll practice it up. But usually it's just cross multiplying. All right. So now what? Integrate both sides to get rid of the derivatives, right? So what do you get on this side? Y. And what do you get on this side? X to the 4th over 4 plus 5x plus, don't forget, C or A or B, I don't care what you call it. Some constant of integration. I don't know that constant of integration unless they give me an initial condition or an initial value problem. They didn't, I'm done. Okay? Any problems with that? Now, just for fun, let's see if Bob is any good at this. Let's see, section 6.3, number 1, right? Where the hell's 6.3? I don't even know where this is. 6.3, number 1. And yeah, that's exactly what we wrote, right? X to the 4th over 4 plus 5x plus C. Ta-da! Okay, that's it. Now notice, this is very powerful because when you solve an equation like x plus 5 is 10, you just get a number. X plus 5 is 6. What's x? If x plus 5 is 6, what's x? This is not a tough question. 1, right? You just get a number. Or if x squared plus 2x plus 10 equals 0, you might get 2 roots, quadratic formula, right? Quadratic equations. Right? Here, what are you getting? You're getting an infinite set of ordered pairs. A whole bunch of x and y pairs that go together. An entire function. This solution is an entire function. Not only that, it's infinitely many, because I don't know what C is. C could be anything. Plug in anything you want for C, and you have a solution. It works. So that's the answer, done. Isn't it true that if you differentiate this, you get that? Basically, that's what we're saying. Okay? All right, let's try it again. We're just going to practice today. 3. dw dt. It doesn't have to be x's and y's all the time, right? So if it's dx, dy dx, you're finding y as a function of x. If it's dw dt, you're finding w as a function of t. Whatever w is, I don't know. 4 rad t. How do you separate this? Just cross multiply, right. Now sometimes you got to get a little more fancy than that, but for now let's say that's all you have to worry about. 4 rad t dt. So now you can integrate both sides because the w is in the numerator on one side, the dt is in the numerator on the other side with the t stuff. That's what you want. The dt's with the t's. I'm separating the variables. I want the t's with the t's, the w's with the w's. There's no more w's, so that's it. Can you integrate this? What do you get on the left? Well, w, actually. It's supposed to be a w. Sorry. All right, and how do you integrate rad t dt? T to the 1/2, right? So if this is t to the 1/2, what do you do with the exponents when you integrate? You add 1, so it's t to the 3/2 divided by 3/2 or multiplied by 2/3. So 2/3 times 4 is 8/3 t to the 3/2. Don't forget the plus c. Here, the no plus c is wrong. Okay, because there are infinitely many solutions here, and there's only one particular solution that goes to a particular point that we're going to solve for eventually. Okay? All right, any questions on 1 or 3? This is called variable separable differential equations of first order. It was first derivatives. Okay, number 4. Just going to practice. You have 5, 10, 15, 20, right? Okay, we're going to do like everything else. dy dx equals 8x plus 1 over x. So how do you variables separate this one? This is the same page, number 2. Yeah, it jumps around a little bit. All right, so all you do is move the dx where? To the right, yeah. So instead of dx in the denominator, dx is in the numerator. Notice it's multiplying all of this. So I need parentheses. So when I integrate, remember this is sort of like a Riemann sum where this is the height of every rectangle, this is the width of every rectangle, right? So it's multiplying, I need parentheses. All right, anti-differentiate, you get? y equals what? 4x squared, right? Plus ln x. And let's make it absolute x. That's going to become important later on this week. We'll see why. Plus a constant. You don't like C? Do A. You don't like A? Do gamma. I don't care. But do something. Okay? Yeah, that's why physics teachers get crazy. They run out of variables very quickly when you do a lot of these. And they start doing alpha, beta, gamma, whatever. Okay, that's it. That's all I wanted. A general solution. You can't get you can't get C without at least one point on that curve. We don't have one, so we're done. All right, number 4. Number 4 says drdp. That was number 2. Did I call it before? I'm sorry, I meant number 2. I'm going a little cuckoo. All right, this is 4. The RDP is 3 sine p. So the variables here are r and p. So what do you do first? Okay, dr is 3 sine p dp. All right, can you anti-differentiate that? What do you get? R is negative 3 cosine. Whoops. P plus a constant. How about alpha? I'm getting tired of C. Whatever constant you want. All right, remember, you can always check this. What's the derivative of negative 3 cosine P? Is it positive 3 sine P? It is, because the derivative of the cosine is negative sine. That's all she wrote. All right, what if they gave you initial conditions? Take a look at number 6. You ready? All right, here's number 6. It says dy dx is 6x squared plus 4x. And y of 2 is 10. So first I want the general solution of any function that fits this description, that has this rate of change associated with it. And then the one of those functions that goes through this point. There will be one unique solution that's a function that goes through this point whose derivative is this. That's the theory behind this, okay? So, what do you write? dy equals? There you go. God bless. By the way, this is a very important application of derivatives and antiderivatives. Differential equations come up in science, in nature, all over the place. Real processes in nature, whether they be in life science or physical science or whatnot. This comes up a lot, so it's a very important tool to have under your belt. All right, so integrate, and what do you get? Y is 2x cubed, okay, plus 2x squared, plus, I don't know, beta, okay? I'm sick of C. It doesn't have to be plus C. It's a constant, okay? Whatever. Call it Martha. What's your favorite constant? Pick one. Z. Well, yeah, Z might be, X, Y, and Z are usually used for variables. Like that might be confusing. But if you know what you're saying, that it's a constant, that's fine. But what's different now is that we can resolve the constant of integration. We can figure out the beta. How do you know what beta is? You can figure out what beta is. How?
Y equals y of 2 is 10.
So that means that Y is what? 10, and X is 2, right? Don't get confused. This is Y of X equals 10. So 2, we're plugging in for X, right? Don't get upset. People get upset here. I don't know why. Function notation. So 10 equals 2 times 2 cubed plus 2 times 2 squared plus beta, or C if you want to call it C. And so you can figure out what beta is, the constant of integration. So 10 equals, well, what is 2 cubed times 2? 16. And 2 squared times 2? 8. And 16 plus 8 is 24. So what's beta? Negative 14. There you go. By Jove, I think you've got it. Whoops, I didn't subtract it. All right, so now the general solution is this. There's an infinite set of curves, depending on infinitely many different choices for beta. But our our choice for beta is negative 14. So y is a function of x. The particular solution is 2x cubed plus 2x squared minus 14. So not only does the derivative of this equal this, right? But if you plug in 2, you're going to get 10. If you plug in 2, do you get 10? It's the only such function that gives you 10. Let's see, if I plug in 2, I get 2 cubed is 8 times 2 is 16. 2 squared is 4 times 2 is 8. Minus 14, is it 10? It is, right? Because that's 24 minus 14 is 10. But we engineered it that way, but, just checking. All right, so that's the particular curve that goes through that point and has that rate of change that we started off with. Remember, this derivative thing is a rate of change, right? Okay. All right, ready for another one?
Yes.
Okay. All righty, 7. I'm skipping the multiples of 5 for obvious reasons. All right, 7 says the PDT is 10 e to the t, okay, and P of 0 is 25. And this strikes me as like a population growth model where t equals 0 is 1990, t in years, and 25 means 25 million muskrats on an island somewhere. I don't know, a population growth model, okay? Can you find P as a function of t? So how do you separate this? Just multiply by dt, basically, right? Is this now something you can integrate? What I call integrable. Yeah, what do you get? 10 e to the t, because remember, the derivative of e to the t is e to the t, and the antiderivative of e to the t is e to the t with respect to t, right? Plus, what's your favorite constant? J? Okay, J. Can we resolve J? Can we figure out what J is? Plug in P is 25 when t is 0. Okay, so 25 equals t e to the 0 plus j. What's e to the 0, by the way? 1. So that's really 10 plus j. How do you get j alone? Subtract 10 and you get, careful, what'd you say? It's 15, right? Okay. All right, so if the general solution is P equals 10 e to the t plus j, the particular solution that includes that point we wanted is P of t is 10 e to the t plus 15. Not only is the derivative of this what we said it was, but it includes this point. If I plug in 0, I'll get either 0 is 1 times 10 is 10 plus 15 is 25. Right? There's two conditions going on. You got to have the right rate of change. You have to have a point on the curve. We're sort of curve fitting this point. Yeah. It's coming up. See the rest of this page? It's coming up. Hang on. You could get something just as simple as this, but usually, it's a word problem. Sometimes. P is a function of t. You can write P if you want, but the assumption being that it's a function of t. Right? So you could say that too. Just to be complete. All right, that was 7, so number 8. All right, 8 says ds dt. This looks like a displacement problem. Doesn't have to be, but look at the negative 32t. Does that sound familiar? Plus 100. Okay. And there's an initial condition. S is 50 when t is 0. I'm going to write it this way. S of 0 is 50. Whatever the units are. I'm thinking this is 32 feet per second, so this is 0 seconds and this is 50 feet, but that's just me. All right, so what do you do first? First step? So ds equals negative 32t plus 100 quantity dt. All right, now what? And to differentiate, and s equals what? Negative 16t squared plus 100t plus, what's your favorite constant? J. Again? Fine, whatever. Some constant, I don't care. As long as you know that's not a variable, right? The only variables here are s and t. All right, so how do you resolve the constant of integration, the j in this case? S is equal to 50 when t is equal to 0. And it's nice when they give you zeros here because things drop out. That doesn't have to be, though. So everything drops out, right? So what's j? You and your negatives. Did you say negative 50?
You're subtracting 100.
I'm subtracting nothing, baby. J is just 50. Everything else is 0.
Oh, 100t.
Yeah. Oh, okay. That's different. All right, so again, that's the general solution, but the particular one is S as a function of t is negative 16 t squared plus 100 t plus 50. By the way, in general, this is half g, right? Remember the negative 32? This is the initial velocity, and this is the initial displacement. So describe this grapefruit to me. This is a grapefruit. I threw it straight up. That's the displacement function for my grapefruit. What does a 50 mean? At 0 seconds, it started 50 feet off the ground, so I guess I was on top of a tree or something. I don't know. Okay? And then what's the 100? That's the initial velocity. That's how fast I threw it. And then that has to do with g. Remember, we started with 32, which was g. Negative 32, negative g. This is negative g over 2. Galileo's general free-fall model is this. V0t plus S0. So this constant of integration has to do with the initial displacement. This constant of integration, we started with acceleration dv dt. We didn't. We started with the SCT. Is the initial velocity. Okay. The example we did originally had 0 here. Yeah. No, you don't believe?
No, I don't understand what you just did.
I'm saying, in general, the free-fall model, according to Galileo, this number is half of negative g. Remember, wasn't g 32, and we always had negative g here, right? Right. And this turns out to be the initial velocity, and this turns out to be the initial displacement. Now, in other words, look. What if I did the original question more in general? What if the acceleration dv dt is negative g? I'm not going to write 32 this time, right? But the initial velocity is something, some number. I don't know what it is. I'm going to call it v0. How do you solve this differential equation? We did this, the very first question we did today, except I had numbers. I had 32, I had 0. I'm doing it a little more general. Still, right, cross multiply.
V equals negative gt plus 0.
Okay, well, right, but now it's not 0. Look, this is what I'm saying. Look, what do you get when you integrate this?
V equals negative g squared over g.
Negative g t squared. I'm sorry, I'm saying it wrong. Negative gt plus a constant, right? J. But how do you get j? We have an initial condition. V is what? Some constant v0, whatever it is, the initial velocity. Whether if it's positive, I'm throwing it up. If it's negative, I'm throwing it down, right? All right, so that's v0. And what's t? 0. So what's c? v0, whatever it is. It's some number, 50 feet per second. I don't know, whatever it is. Okay? So the general solution is v is negative gt plus c. But the particular solution is v is negative gt plus v0. All right, so when we originally did this, our v0 was 0, but it doesn't have to be. Right, when I dropped the stone, the initial velocity was 0. I didn't throw it. Right? All right, but wait, this is a differential equation too, because v is the rate of change of what? Not t. Of your position, your y if it's vertical, your x if it's horizontal, your s in general. I'm going to call this ds dt. So, what now? What do you do to solve this? For s of function of t. So ds is negative g t plus v0 quantity times dt. All right, integrate both sides of this. What do you get? gt squared over 2 plus v0t plus some other constant. Now, if I give you an initial condition like s at time 0 is some s0, some number, some initial displacement off the ground, 100 feet, something, right? Can't I now solve for c? What do you plug in for this? S sub 0, some number, whatever it is, 100 feet, 20 feet, whatever it is negative g times, what's t? 0 squared over 2 plus v0t, and again t is 0, plus c. So like in the last example, everything drops out, and what's c? S sub 0. So the general Galilean displacement curve is s as a function of t is negative gt squared over 2 plus v0t plus c, which is s0. It's a constant proportionality with how fast you're falling with respect to t square. It happens to have to do with half of the acceleration due to gravity. G is acceleration due to gravity. How fast you're falling. How fast your velocity is changing as you're falling. Negative 32 feet per second literally means your velocity changes negative 32 feet every second. So you start at rest, then a second later, your velocity is 32 feet per second. A second later, it's 64 feet per second. A second later, it's, 96 feet per second, and so forth. That's what the acceleration is. That's what g is. Okay? Okay, so when I say that our solution to the previous question means that we started 50 feet off the ground with an initial velocity of 100 feet upward, right? Positive velocity means going up. That's where I got it from. I'm matching it up with this. And it wasn't obvious there, but hopefully it's obvious now, right? All right? Now, this is the Galilean freefall model, which is flawed. Why? Because we're assuming a certain constant g at sea level, right? Or a constant g wherever, and we're not dealing with air resistance. We're assuming air resistance is negligible. As it turns out, the force due to air resistance gets greater and greater as you go faster and faster. So the higher you start falling, the faster you get, eventually you end up with something called a terminal velocity, where the force due to air resistance cancels out the force due to gravity, and your velocity then becomes a constant. But for small values of v, for small velocities, this is pretty good. So if you're not falling too far. If you're falling from, an airplane 5,000 feet in the sky, this is probably not accurate. Okay? Alrighty. So that was 8. Okay. Any questions through 8? Practice, practice, practice. Okay. How about 9? Just for fun. 9 says, what if dy dz, so we're going to find y as a function of z, equals 2, yeah, that's very good, 2 plus sine z. And you get an initial condition. Oh, it's not a y, it's dq, sorry. It's dq dz. dq dz. So we're going to find q as a function of z. And they give you q is 5 units, whatever they are, when z is 0. So in other words, q of, that's a q, dang it, q of 0 is 5. I like to use that notation, same thing, right? So what are we going to do? dq equals 2 plus sine z dz, right? All right, now what? Anti-differentiate or integrate, right? Indefinite integral gives q equals 2z, that's a z, okay? My z's have a line through them, okay? You can live. Is it negative cosine, you said? Yeah. The derivative of the sine is the cosine, but the antiderivative of the sine is the opposite of the cosine. Plus, I don't know, b, okay? Okay, are you done? No, because you can resolve b. There's a unique curve that has that slope, or that, slopes of the tangent lines, and has that point. So, what do you plug in for Q? 5. What do you plug in for Z? 0. And does everything drop out this time? Careful, it doesn't always. 5 equals 2 times 0, that drops out, minus the cosine of 0. Remember the cosine of 0 is? 1. So this is really 0 minus 1 plus b. So what's b? 6. Good. All right, there you go. And so that's our general solution right there, right? But our particular solution is q as a function of z is 2z minus cosine z plus 6. And there you go. Okay? Any questions how we arrived at any of these results? Is this terrible? It's basically integrating, right? Yeah, that's basically it. Okay. All right, so how about we do some word problems. Look at number 12. A tomato is thrown upward from a bridge 25 meters above ground at 40 meters per second. In other words, that's the initial velocity, right? Give formulas for the acceleration, velocity, and height of the tomato at time t. How high does the tomato go, and when does it reach this highest point? How long is it in the air? So not only are we calculating how long it takes to get to the top and where that is, but how long it then takes to get to the ground after that. So it has an initial displacement of 25 meters. We're starting on a bridge 25 meters high, at least when I let go of the, whatever it is, tomato. It's 25 meters high, right? And then it says the initial velocity is 40 meters per second. What does that mean? That means, right, that means I'm throwing it upward. I could actually throw it down if I wanted to, right? It could be a negative 40, okay? Or it could be 0, whatever. But okay, so now we know what we're talking about. So here's 12. And let's change our color just for fun. All right. Okay, so what is the acceleration equation? dv dt, that's the acceleration, right? The rate of change of velocity is what? And give me a number, we know it. And it's not 32. It's not 25. It's not 16. 32 feet per second per second. Here they're talking about meters. 9.8 something. Let's say 9.8. But yeah, it could be more accurate than that. But let's say 9.8. All right, so we're going to say negative 9.8. It's negative g, right? But in this case, in meters per second at sea level. Now, of course, it's not sea level because we're 25 meters above the river on the bridge, but close enough, right? It's negligible. The difference would be negligible. All right, so there's my acceleration. How do I get my velocity function? Realize this is a function. This is a of t is negative 9.8. The acceleration is constant. This is known as a uniform motion problem. The acceleration is constant. Okay? If the acceleration were not constant, if there were a jerk involved, not a person, right, that's right, exactly, then there would be a non-uniform motion, right? That's what they call those problems. Anyway, so that's a of t, it's a constant, right? The acceleration is a constant. But how do you get v from that? dv equals what? Negative 9.8 dt. Okay, then you integrate, and you get negative 9.8 t plus a constant. Now remember, they gave you the acceleration to get the velocity, but we're going to use the velocity to get the displacement. I'm going to need two constants of integration. I'm going to call one a and one b for convenience sake. That's all, okay? What was that? Okay, anyway. So how to get v? How to get a? We got v. Don't we have an initial velocity? What did they tell you? 40, right? Didn't they say, in fact, that v of 0, the initial velocity is 40 meters per second? They said that. So plug in what? 40 equals negative 9.8 times what? 0. And so what's a? Happens to be 40, but didn't we talk about this? That second constant has to do with the initial velocity. Did you see that? You didn't see that? Okay, good. I don't know. I'm pointing here, and my pointer went for no reason. Okay. You didn't see that? Okay. This has to do with the acceleration due to gravity. This has to do with the initial velocity, right? Okay, we knew that. Okay. So v as a function of t is negative 9.8 t plus 40, right? But what's your displacement curve? V is itself a derivative, right? Of what? Of the displacement. Now we're throwing the thing vertically or something, so I guess we'll call it dy dt. I didn't say it was vertical. Let's say ds dt. I don't know what the exact displacement is. So let's say ds dt is the velocity. Be careful, the nomenclature here. Velocity is a vector quantity. I don't know if we're talking about the vector here. I guess we could, because if we say the vector, we're talking about a distance. Yeah. Velocity is a vector quantity. Speed, the magnitude of the vector, is how fast you're going, right? But I don't know if we want to get that tedious about this. All right, so this is ds dt. Let's not worry about the direction. Equals negative 9.8 t plus 40. I didn't change anything. I just said what v means, right? Now what do? Derive? Derive doesn't mean much, actually. Some people think that means differentiate. Cross multiply and then anti-differentiate. I wouldn't say that's deriving, but okay. I mean, deriving is a general term that covers a lot of different things you would do to get the answer. So yeah, you're right. But what does it mean? I don't know. All right, so now anti-differentiate. And you get S is? Isn't that negative 4.9? Huh? T squared, right? Yeah. Negative 4.9 t squared plus 40t plus, I used A, so I'm going to use B just to make the point that it doesn't have to be the same, right? But don't we have an initial displacement too? What was S of 0? No, that was V of 0. 25 meters high was the bridge, right? So that means I can, to figure out B, I'm going to plug in S as what? 25, while T is 0. I'm making a big deal of which is S and which is T because people mix this up. Okay, negative 4.9 times 0 squared plus 40 times 0 plus B, and this is 4.9. Dang it, that's not much better. Okay. And so that tells me that B is 25 because this all drops out. These are all zeros. So B is 25. So the particular solution for S of t is negative 4.9. Dang it, with the 9. Why is it doing that? 0.9. Dang you. 0.9. There you go. T squared plus 40t plus 25. And again, we said when we get to the displacement curve in the Galilean model, this is the initial displacement, this is the initial velocity, and this is half of the acceleration due to gravity. And yeah, that all makes sense. Okay, but now let's answer the question. Part A says, find A of t, V of t, and S of t, and we did. Find the acceleration function, there it is. Find the velocity function, there it is. Find the displacement function, there it is. That's part A. Part B, how high does this tomato go? We want to maximize the height function, right? The SDT or the HDT, whatever, right? How high you are. How do you maximize stuff? You find where the derivative is 0 or undefined. Well, what's the derivative of S? It's V. So set this equal to 0, solve for t. That's when it hits the min or the max. I don't know. You got to think. All right, what it is. But let's see. Let's set this equal to 0. So let's continue. V of t was negative 9.8 t plus 40, right? I want to know when it's 0. It's not undefined, is it? Are you ever going to divide by 0 or square root of negative? Or no. Depending on what you plug in for t now. So when it's 0, and so how do you solve for t? Subtract the 40, so negative 9.8 t is negative 40. So t is 40 over 9.8, whatever that is. 9.8 is a little bit less than 10. So when you divide 40 by a little bit less than 10, it's a little bit more than 4. How much? 4.08 something? Okay. I'm going to have round off. I'm going to say this. Okay? And this is in seconds. Okay? Now think about it. If I pick a number smaller than that, is the velocity positive or negative? Like you said, what was it? 4.08? So I pick like 1. Right? I'm doing a sign line test in my head. If I pick 1, is this going to be positive or negative when I plug in 1? Positive. So it's increasing. Then there's a horizontal tangent, right? Then if I pick something bigger than, what was it, 4.08, pick something like, I don't know, 10. And it's going to be negative. So this is going to be a max, isn't it? At this t, s is going to be a max. So how do you figure out the highest point? Plug it into s. S of 40 over 9.8 is what you want. And that's, here's s, right? So it's negative 4.9 times t squared, which is 40.9 over 9.8 squared, plus 40 times 40 over 9.8, just a little bit more than 4, right? Plus 25. So let's see what the zenith of my tomato is. Okay, now we have to get a calculating device in here. Where is it? Come on, wake up. And of course, he's asleep. That one day he woke up. I don't know. Waking up. You're waking up today. Tick, tick, tick. Put some toothpicks in your eyeballs. Oh, jeez. All right, so you said you saw Stand and Deliver, right? You remember that scene where the kid falls asleep in the middle of class? And he comes up and pinches him with his pointer. And the guy's waking up. He's like, I was dreaming about dolphin in an imaginary ocean with eyes. And it's like, oh, back to sleep. That was a good dream, right? Remember that, right? I'm quoting Stand and Deliver, that movie about Jaime Escalante. He said he saw it. Yeah. Is that when it came out? It actually came out originally on PBS only as part of, I don't know, some show like Great Performances or American Performances or something like that. And then it became so well known that they released it in the theaters. So, anyhow, what am I doing? I want to know that time. What was it? 40 over 9.8. So what time is that? It's 4.08 something. Okay, I'm going to store that as, I don't know, alpha A. Okay? Now, in y, I'm going to put in my function, just for fun. It was negative 4.9 t squared, but I'm in function mode, so I've got to use x, plus 40t, I'm going to use x, plus 25, right? Isn't that our solution? Our displacement curve, right? Okay. I want to know what that is when t is 4.08. So I'm going to do vars, y vars function 1 at alpha a, where I stored that answer. And it started at 25 meters, and it got up to 106 something meters. Notice how I'm avoiding round-off error. I didn't plug in 4.08. I plugged in 4.08, blah, blah, all the decimals I can get in the calculator. And there's more than that displayed. A fixed 9 is what's being displayed, but there's more in RAM, I think, than that. Okay? And it actually goes to like 11 or 12 digits with some accuracy. So, all right, so that's the answer. That's the zenith. That's how high my tomato went. That was part A and part B. What's part C? How long does it take before it hits the ground? How long is it in the air? Well, we know it went from 25 meters up to the 106 meters. I shouldn't say that. 106 meters. And means decimal. In 4.08 some odd seconds, right? But then it has to fall, how far? It went up 25 meters, but does it fall 25 meters? I'm sorry, it went up 106 meters. Does it fall 106 meters? If it hits to the ground, it goes 25 meters more, right? I need to know when my S is 0. I need to solve when S is 0, when it hits the ground. So what S of 0 is 25, right? S of 4.08-ish is 106. S of what is 0? That's the question. Okay, so let's find out. So this was, what the hell was it? 106.633-ish, let's say. 106.633, and this was in meters, right? Okay. All right, so now what is left to do is to figure out when S of t is 0. We want to solve for t. But S is negative 4.9 t squared plus 40t plus 25. Now you can solve this exactly with a quadratic formula by factoring or something, or just graph it and see what the calculator says. Why don't we do that? Let's use a calculator. So I already put this into y equals. What I need to have is a complete window for x greater than 0, for t greater than 0, right? So let's see, if I do zoom 4, is that any good? No, because remember that S of 0 is 25. That would be the y value here is way off the screen. So it has to go at least up to 25. In fact, it goes up to 106 something, right? So I'm going to say, okay, my window, I'm going to make my x min, just for symmetry's sake, I'm going to say negative 200 to positive 200 so I can see the 106. And then I can see where it hits the x-axis and I can get zeros and stuff. Okay, and so an y scale of 100 would probably be better. And graph that. Now notice we're not interested in negative x's because that's negative time. T equals 0 is when we start throwing. So I don't really care about negative x's or negative y's. I'm only worried about the first quadrant and where it hits the axis, okay? So this is where it starts at y equals 25. This is the max up here at 4.08 something. That's the max, 106 something, right? But I want to know how long it takes to hit 0. And that's not a good window, is it? All right, so let's play with the window. I don't need negative x's. I don't need, I guess I'll keep negative y's just to see the zeros easily. How long do you think it takes? Guess. 10? All right, I'll just double this. That's almost 10. All right, so that's a good window. There's the 0 that I want. Okay? So if I do second traces calc value at 0, I'm at 25, right? Right there. If I do value at 4.08 something, I'm near the max. That's round off error. That's not the max. It's damn close. Can you get that on here? Can you get the calculator to get you the max? You can, right? You can do second traces calc and then max, right? 4. And what you do is you pick a left bound that's definitely before the max. I'm thinking here. And then a right bound that's definitely after the max, and it's going to actually find the zeros of the derivative with the tangent line slopes change sign. And we get at 4.08, 163, whatever, and that's how many seconds, and 106.633-ish meters, same result, right? But what I want is this 0. See when it hits the ground. Okay. So second traces calc, 0, find the 0 near there. Come on, get over there. Move. Okay, so a positive y, let's have a negative y, and there should be a 0 somewhere in between for continuous curves. And we get, it takes almost 8 3/4 seconds. So that's the answer. T is about 8.747. And that's the answer to part C. All right, any questions on solving differential equations involving motion, acceleration, velocity, displacement, Galileo's model, right? Is this okay? Are we okay with this? Any questions? Let me know. Okay. All right, I think that's good for YouTube because aren't we, how come I can't see? There it is. Yeah, all right, we're almost done with it. So see you, YouTube. Hope you got some out of that. Have a nice day.